Welcome, everyone. Consider this explainer your fundamental masterclass in discrete probability. I want you to think of me as your senior process engineer for today, here to guide you, my future colleagues, through the absolute, sometimes gritty realities of quality control on the factory floor. You see, we aren't just learning math today. No, we are learning how to save millions of dollars, how to prevent catastrophic failures, and most importantly, how to ensure the sheer safety of the products we manufacture every single day.
Okay, let's dive right into this. On a chemical plant floor, a single defective badge can literally ruin an entire production line. It is incredibly high stakes. But remember this: probability is our absolute ultimate tool. It is exactly how we take unpredictable, wild chemical chaos and engineer it into something highly controlled, safe, and efficient.
All right, here's our roadmap for today. First, chemical quality control. Second, binomial, samples with replacement. Third, Poisson, events in intervals. Fourth, hypergeometric, samples without replacement. Fifth, the decision tree. And finally, number 6, the power of prediction. Remember, we are building a mental toolkit here for diagnosing real-world process failures. Let's get to it.
Section 1. Chemical Quality Control, Grounding the Math. Before we look at any complex statistical formulas, we really have to understand the physical reality of our variables on the floor. A continuous variable, well, that's like a valve opening gradually across an infinite number of positions. But discrete probability, which is our entire focus today, deals with discrete variables. Think of a valve that can only be fully open or fully closed. We're dealing with specific, countable events, like counting individual molecules or checking if a single component is defective or not. There are no infinite fractions here, just clear, distinct yes or no outcomes.
Moving right along to Section 2, binomial, samples with replacement.
Introducing the very first tool in your new Process Engineer Toolkit, the binomial distribution. We use this to predict the probability of a specific number of successes across a set number of independent trials. Here is the catch, though. There can only be two outcomes, success or failure, and the probability absolutely must remain constant for every single trial. For this model to work, the events have to be entirely independent. In a factory setting, this means we're either sampling with replacement or, and this is super common, we're testing such a massive, continuous population that removing just one little sample doesn't change the odds at all.
And this brilliantly illustrates how we apply the binomial distribution out in the real world. Imagine we're verifying pharmaceutical safety for a polio vaccine. To actually be effective, a single shot requires at least 67 V polio molecules. Now, our manufacturing baseline produces a massive, huge vat with exactly 75% V polio molecules. So our probability, our little p-value, is 0.75. We then draw a sample size, our n, of 100 molecules per syringe. Our goal here is to find the probability of getting at least 67 successes. That means anywhere from 67 all the way to 100 V polio molecules in that one single syringe. And here's the key takeaway. Because the total vat we're drawing from is just so massive, pulling out 100 molecules doesn't shift that 75% baseline one bit.
Crunch those numbers through the binomial formula, and boom, we get 97.24%. That is the probability that this specific syringe will successfully protect the patient. As an engineer, you can look at that number and confidently tell your quality assurance team that the production line is, in fact, delivering safe, effective vaccines.
All right, on to our next model in Section 3, Poisson, events in intervals.
So what if you don't actually know the total number of trials? That's where our second tool comes in. It handles situations where we don't know the exact trial count, but we do know how often an event happens on average. The Poisson distribution is absolutely ideal for modeling rare, discrete events that occur within a specific interval of time or space. Think about a continuous stirred tank reactor, or maybe a massive fluid sample where checking every single molecule to find a total trial count n is, frankly, physically impossible. Instead, we just rely on the average rate of occurrence.
Let's look at a medical diagnostic scenario to make this concrete. Say we're testing for the prego hormone. We know our baseline. Naturally, there's exactly one hormone molecule per 10,000 in a sample. That's our rate. Now we extract an interval, a sample of 5,000 total molecules. To use Poisson, we first have to find our expected value, which is represented by the Greek letter mu. We literally just multiply our rate, 1 in 10,000, by our sample size of 5,000. This gives us an expected success rate, our mu, of exactly half a molecules for this specific interval.
Plug that expected value right into the Poisson equation, and we find there is exactly a 30.3% probability of finding exactly one prego molecule in this specific 5,000 molecule sample interval. Notice how we didn't need to count every single molecule in the patient's entire body.
We just needed the rate and the sample interval to find our probability. It's a huge time saver.
That brings us to section 4, hypergeometric, samples without replacement.
Now, what's really interesting here is the stark contrast between the binomial and hypergeometric models. With binomial, probability stays totally constant. But in the hypergeometric model, we are dealing with small, finite batches, and we absolutely do not replace the sample after drawing it. Guys, this is a massive distinction. Pulling a component from a small batch physically alters the probability for the very next draw, which completely violates binomial rules. So this is your go-to tool for industrial lot testing.
Let's walk through a classic lot rejection scenario right on the factory floor. A machine produces a highly specialized batch of 40 components, so our capital N is 40. We know historically there might be 3 defective parts hiding in this batch. That's capital K. We pull a sample of 5 parts for destructive testing, which means, yes, we get to break things, and they definitely do not go back into the batch. That makes our lowercase n equal to 5. We want to find the probability of drawing exactly 1 defective part, our target x, to trigger a lot rejection. Because we're pulling from a small pool without replacement, the odds actually shift with every single part we pick up.
Run the hypergeometric math, and it reveals a 33.65% probability of finding exactly 1 defective component in that 5-part sample. As a process engineer, understanding this exact percentage is absolutely crucial. It helps you mathematically balance the real-world cost of destructive testing against the terrifying risk of shipping a bad lot to a customer.
Let's pull all of this together in section 5, the decision tree.
Now that we have all our mathematical tools, how do you actually know which one to grab when you're standing out there on the factory floor? I want you to mentally walk through this diagnostic decision tree every single time you face a quality control problem. Step 1, are there only 2 discrete outcomes, like pass or fail? Step 2, do we know the total finite population size, or are we dealing with a massive continuous flow? And step 3, are we replacing the sample after drawing it, or are we throwing it away? Your answers to these 3 exact questions will completely dictate your math. So the crucial point really all comes down to this matrix. If your population is massive or you have replacement, deploy the binomial model. If your population is unknown, but you're looking for rare traces in specific intervals, use Poisson. And if you're dealing with small, finite batches without replacement, you absolutely must use hypergeometric. Master this matrix, and I promise you, you will always deploy the correct mathematical model to diagnose a process issue.
Finally, let's wrap things up with section 6, the power of prediction.
As future engineers, your daily responsibility isn't just running equations on a whiteboard. It's making high-stakes, real-time decisions that keep the plant running safely. So, I'll leave you with this provocative thought. If probability is the key to turning chemical chaos into a controllable process, which distribution will you trust when a single defective batch threatens to shut down your entire plant? It's your job to know the difference. Thank you for joining this explainer of our source material today. Now go out there and engineer the unknown.